Hello everyone, and welcome to a video where we're going to be making a shooter game. We're going to be making something just like this, where we have a player at the bottom, able to shoot these bullets up towards a wave of enemies that are moving towards us, Space Invader style. We're going to be using the Pixel game engine for this project, as I like to use, and we'll be writing in C++, of course. We're going to get started with how we make this. First, I'm going to make a new project in Visual Studio. We're going to call this our shooter game. First thing I'm going to want to do is set up the OLC Pixel Game Engine header file, which is going to contain our main engine. I'll have to go on the OLC One Lone Coder Pixel Game Engine website and grab the source file here. And I'll include a link to this as well. Once I have this copied in, and I only found out about this recently, but in the header file, it actually contains the example, and I did not know this until recently. So if you go past the update notes, right after it says example hello world program is actually included straight in the header file itself. So that's very nice. I used to just go on the repo and grab it every time until I realized I could do this. So I'm going to make a new CPP file. This is going to be our main game program file. I'm going to call it shootergame.cpp appropriately. After I paste this in and remove the comment, let's clean it up a little bit. Here's our example, and let's do some indentation. If we go to Edit, and we choose Advance and Format Document, shortcut is Control-K, Control-D, Visual Studio will auto-format it for you. So starting from this example-based project, I always like to run it, make sure we see our flashing pixels here. That's how OLC Pixel Game Engine Hello World works. We're ready to start modifying this and making our game. First thing I'm going to do, and what I like to do, is change the example class to be the name of our game, or something similar. So I'm going to go ahead and press Control R twice here, and this allows me to refactor. If you also right-click on the class, you can select Rename from here. So I'm going to change it from example to shooter game. When I hit preview, it's going to tell me what's about to change. I'm going to hit apply here, because I want to change these things. Alright, so let's talk a little bit about the game real quick. Here I have a little set of sprites, and I want to use these little alien guys here from the sprite sheet. And I also have this little player here. And you'll notice I put them all in one file. One thing you can do, and it might be simpler to think about, is to put these into separate files each. But what if you have an even larger sprite sheet? Do you really want to separate them out manually? Sprite sheets are great because we can just load in one image and reference different pixels of it in order to produce the image we want. However, it does require a little bit more outward thinking on your part in order to make sure you have what you need. So how are we going to manage this? One thing I think we should do is come up with a concept of a rectangle. So this rectangle will allow us to define an X, a Y, a width, and a height in the sprite sheet, and then we'll say, okay, draw those pixels specifically. So let me open this up in an image editor, actually. That will help us a lot. Hello, blah. So inside of here, we have our little sprites. So I'm interested in grabbing the image here. So this image starts at pixels. I'm just looking at the bottom here of my image editor. Pixel coordinate 5, 22. I'm just going to annotate that somewhere in my program for now. This is 5, 22. And the size of this box, which it also tells me, is 11 by 9. So this first alien is located in the sprite sheet at coordinates 522 and has a size of 11 by 9. And we can do the same for the other two aliens here. And kind of define them that way. So here, we have it at 1922, and it's 12 by 6. And for the third alien, it's at 34, 20, 11 by 8. And most importantly, we need our little spaceship, our player spaceship. So up here, it starts around 35, 6, and is 11 by 7. So I wrote in the comments here some coordinates and things we'll need. First thing I'm going to do is come up with a rectangle struct. So I'm just going to call it rect, short for rectangle. We know we want to store the x, y, and with height coordinates, and they can all be numbers. So I'm just going to declare them as integers, like so, x, y, with height. Let's declare them in that order. That way when we define them, that's how it's going to be. So because we want to create a rectangle, we're going to define those rectangles inside of our shooter game. So I'm going to type rect, and we're going to call this alien1, and I'm going to set it equal to some values. By using these curly braces, we can define our struct with the parameters we specified here. And so I'm just going to copy the numbers I wrote earlier. So x and y is 522. I'm actually going to press tab just for the sake of seeing that, yes, these are the positions and these are the size, and I've separated them. The tab doesn't have any consequence. The compiler just ignores that. I'm going to do the same thing, but for the player as well. Or I'm not going to call it player. I'm going to call it the ship, more specifically. And we can fill in all these numbers here. And now we kind of have this structure set up for us to define our actual sprites. So I think the next cool thing we can do is try to use these rectangles to draw those specific sprites on the screen. Sigception. So the Pixel game engine comes with a function that allows us to draw specifically at certain pixels within an image. However, we don't have that image loaded yet. So the first thing I'm going to do is make a new sprite. This sprite is going to be our tile sheet. That's what I'm going to call it. And I actually made it an, oh, excuse me, we have to put OLC sprite to say it's from the OLC Pixel game engine. So I made it a pointer, and let me change this example to shooter game here while we're down here. But we need to initialize our sprite inside of the constructor. Or, ooh, actually, no, don't do that. Don't do that. Do it on user create. Once the engine initializes, then we can load our sprites. So Tilesheet will be equal to a new sprite, which creates a pointer to it. And inside of new sprite, we define where our image is located. So I'm going to actually go ahead and open up the location where our... Actually, let me do it this way, just to show that. So in shooter game, if I right-click, and I go to Open Folder in File Explorer, this is where we have to put our stuff. So if you're ever confused where to put stuff, that's how you do it. Here, I'm going to copy-paste my image. It's right now called 8-bit aliens.png. I'm going to rename it to the tilesheet.png. So now, when I type in my file name, it's going to be tilesheet.png here. Oh, and I forgot OLC again. Bad habit of mine. So tilesheet.png is located here, so that is where we're referencing it. You can see our CPP file and our header file is already in here as well. So all your project files go in here. Once we've done that, our tile sheet is now loaded and we can start drawing from it. Let's just draw it at first, just to make sure it's there. So the OLC Pixel game engine comes with a draw sprite function. The draw sprite function takes a couple of parameters, as we can see by the pop-up here. So it's going to be the X position. We'll draw it at 0, 0, the Y position, followed by the sprite pointer, which is called Tilesheet. And optionally, there are scaling parameters. So I'll actually use this one so we can see it nice and big. And you can also flip it if you want to. We're not going to flip it though. I'm going to hit the play button now just to see if it pops up. You can see our tile sheet successfully shows up here in game. So we know we loaded the sprite correctly. If you do run into problems with it, make sure you check your file name. That is correct. Make sure you're using the right sprite, the right variable, and make sure the tile sheet is defined in your shooter game class so that it can be used. You can see I defined the struct rectangle outside of here. It's not part of shooter game, at least not directly. So it's going to be an outside class brought into the shooter game class. Right now it's a dependency of it. If we were to move struct rect down here, our program will not compile now, even though it looks like, hey, there's no errors. It won't compile because the linker reads from top to bottom, and when it gets to rect, it knows it exists, but it doesn't know what it's defined as yet. So since it doesn't know what it's defined as yet, it doesn't know what to do with all these. I make that important distinction because order matters when you're programming. And these are some common pitfalls that you may run into if you try to add and mess with things as you're adding things to your game. So now that our tile sheet is drawn, how do we draw these specific portions of the tile sheet? We'll be modifying our draw sprite function to use draw partial sprite. Draw partial sprite takes different parameters though, so I'm going to be redoing them here. First, it takes a position. We can define an inline set of coordinates by using these curly braces to initialize, just like we did with the rectangle up here. We make an initializing list of all of the parameters we want. So a position takes 2 arguments, it's x and y. Interestingly enough, we know the x and y coordinates. So for example, if we want to draw this alien, we would use alien1, oh, I deleted the braces. Alien1.x for its x position and alien1.y for its y position. And they'll directly take these values I typed in earlier and plug them in here. Our sprite once again comes from Tilesheet, and now it asks us for a source position. So within the Tilesheet, oh, so I made a mistake. This coordinate actually references where in the Tilesheet to grab that data from. So we want this to actually be here. The first set of coordinates is where to draw it on the screen. Like, let's draw it offset by 32 by 32 pixels from the top left corner. But the source position of the subimage comes from there. And finally, the size of the subimage is defined by the width and height parameters of our rectangle structure. And once again, for now, to make it seem big, I will scale it by a value of 4. And finally, it looks like I have this lingering brace here. Delete that, put a parenthesis at the end to close out our draw partial sprite function. If I did everything correctly, this would have drawn the alien on screen, the alien 1, and it has. Now the nice thing is we can replace any of these alien 1s with a different value. So let's try alien 3 and we'll get the sprite of that particular alien. So this one looks different. And as another demonstration, instead of drawing the aliens, we could also draw our ship in the same manner. So we have defined a structure where we can specify within a tile sheet any particular coordinate of sprites. And if we've done it right, it ends up on the screen like this. So that's excellent. Now we get to talk about a little of the game now that we know how to draw these. It might be nice to split these up into little functions. That way we don't have to keep typing all this out every time. For example, this is required in order to draw the player, right? So why not make a little function called drawPlayer inside of shooter game that does this. That way we don't have to type all that every time. We can type just drawPlayer. But more generically, and I think this is a very important connection, if we were to replace ship with another rectangle, we would be able to draw any sprite and have a more useful function that does multiple things. Draw subsprite. So I'm going to call this function draw subsprite and have it specify a rectangle for the sprite. Now, instead of changing these, because you'll notice, if we want to draw an alien, what do we change? We change these. If we want to draw the player, we also change these, right? So why not have it be a variable, and then draw subsprite accepts a variable that changes these for us. Now we have a useful function where we can draw whatever we want. We can draw an alien 1, or we can draw an alien 2, or 3, or ship. But then we realize it's still not that useful, because if we do something like this, we're just drawing one sprite at the same position over and over. So that sprite got overwritten by alien 3. That's not as useful, unfortunately. And the thing we have to change is this position here. So if we include a position parameter, we're going to use the OneLoneCoder Pixel Game Engine's vector2d class, and the I stands for integer, so it's a 2D integer vector. And this is going to be define the position for us. So the first argument is position, and we can go ahead and directly replace that 32 by 32 with pos. That immediately makes this way more useful, as now we can type in, I want this alien at position 24, 24, and I want this alien at position 64, 64. And now we have an inherently useful draw function here, where we can draw any given sprite that we provide, subsprite I should say, at any given position. We'll be using this for the next portion of the game. The first thing we want to do is make a way to draw a bunch of enemies on the screen and a player on the screen. Typically that's what we like to do, right? Get our player on the screen, show something. Now right now we don't have anything to do with handling objects. For now, I'm going to create the player's position inside of the shooter game class. Later we'll clean this up a little bit and you'll see why. But for now, we're going to call this the player position, player pos. And we can set a default value to it. You'll see these curly brace things being used everywhere because I like using the vectors, so we're going to keep using them. You can split them up into player X and player Y, but I think using what the features provided by OneLoneCoder Pixel Game Engine will give you a lot more cleaner looking code. Because these are coordinates, so you want them to kind of be provided together all the time. Let's put the player's position. If I go down here, this is the window size, 256 by 240. I think a good starting position for the player would be half that. So let's try 128, and then put it near the bottom of the screen. Something like 200, I think would be a good spot for the player to be at. So we'll be using this variable to indicate where to draw the player. So if I go ahead and call draw subsprite, and I put player position in place of what we typed earlier, and I draw the ship there, we should see the ship drawn at that location. Very good. But you'll see it's not actually centered, even though I said I wanted it in the center. Well, 256 divided by 2 is 128, so I didn't do my math wrong. What I did do wrong is we're drawing it from the upper left corner here. If you want to center a sprite when you draw it, then you have to draw it with an offset. So because we know the width and the height, or since we know the game draws everything from its upper left corner as a reference, in order to draw things centered, and I've talked about this in a Pong video I made earlier, you have to offset it so that it's centered at where the position originally was. And you can see there I intentionally dragged it back to the left, as that's what we would be doing. If you want to vertically center, you'd go up as well. So that is essentially the operation you are doing to center sprites. We know the width and height of our sprite because we defined that inside of our rectangle we made earlier. So we already have all the values we need to offset and draw our sprites centered. Here in pause, I'm actually going to subtract, and I'm going to type OLCVI2D to specify a new vector 2D within here to subtract from, and I'm going to say subtract the sprite's width and the sprite's height divided by 2. One really powerful thing that vectors allow us to do is do mathematical operations on them. I can take one vector and subtract it from the other, and it'll subtract both the x and the y components of it at the same time. I can also do divisions on them or multiplications on them. That way I can adjust both values at the same time without having to type them out manually. It would be pretty annoying if I had to type in pause.x minus sprite.width divided by 2, comma, pause.y minus sprite.height divided by 2. It's a very nice feature of these vector 2D classes from the OLC Pixel game engine. So if you look right here, it's still not quite right. And that's because we've scaled our sprite by 4. I've made it really, really large. That was mostly for demonstration purposes, and I'm going to remove it now. But if you wanted to use a scaling, you would have to multiply the width and height by whatever your scale is. So I would have to multiply by 4, then divide by 2 to center it with that sizing. You can see now it's centered using that scaling. But I don't intend to use the scaling, so I'm going to actually remove that portion. And so we're now back to a normal size because we're going to have to make our game with a lot of enemies on the screen. So I've essentially zoomed out the game by making the player tiny, but you can see the sprite is now centered with that math. Moving on, we have to draw some enemies on the screen. We want a lot of enemies. We want a wave of them. Since we need more than one enemy, we can't just type in enemy position because, well, that's the position of one enemy. What if we want 2 enemies? Enemy position 2? Enemy position 3? Enemy 4? Enemy 5? No, we're not doing that. We're going to be using a container that holds all these enemy positions for us. We're going to be using a standard vector, which is simply a dynamic list where we can add to or remove from any thing we want from it. Since these are called templates in C++, and for a vector specifically, inside the template parameters here, we're going to be using a vector 2D. So we're essentially saying make hold a bunch of vector 2Ds for us. And I'm just going to call this enemies for now. Enemies have a position. And so what we're going to be doing with this vector is we're going to be adding a bunch of positions to it. Then we're going to loop through that vector and draw a bunch of enemies on the screen. In onUserCreate, since it's only called at the beginning of the program launching, we're going to specify a certain amount of enemies on the screen to draw. So I'm going to start with a for loop here. I'm going to say, let's draw 16 enemies in a row. So this is a for loop. It's pretty standard. You have I equals 0. Until I reaches 16, you increment it by 1 and do what's inside of this block. Vectors have a function called pushback. It allows you to insert something at the end of a vector. And you have to specify, in this case, a vector 2D you want to add. We already know how to make vector 2Ds using the curly brace initializers, and we can specify where we want to draw them. Now, the position is not going to be static. Like, I don't want all the enemies to be in one spot. I want them to all be next to each other, back to back. So, the size of each alien is about 11 pixels or 12 pixels wide. So I'm going to separate them by 16. So the way we would do this is we would add to our x position 16 multiplied by the I value here. As I increments from 0 to 1 to 2 to 3, you can see the I will go up, and that will multiply it by 16, putting them in a grid. To handle the drawing, we do something similar. We use a for loop again, but C++ vectors have or iterators in general, have a built-in syntax for going through them. So, our list of enemies each contain a vector 2D. So we can pull them directly by saying lcvi2d, putting the ampersand there so it's a reference, and we'll talk a bit more about why that's important later. And we'll just call the value we pull from it enemy. And then I'm going to put colon enemies. The way you would read this is from the enemies list, pull each vector 2D and store it in enemy. So now that we know what the coordinates are, we can draw a subsprite again, but now at the enemy position. And instead of using the ship subsprite, let's use something like alien 1. Now that we're done, I'm going to go ahead and run this. We'll see what we got so far. Well, it does look like we have a row of enemies, and they're all being drawn. So it looks like that worked. Again, we have a loop of 16, iterate through that, add 16 each time, and push that value into the enemy list. Then in on-user update, we are drawing that list over and over. So all 16 enemies appear in a row here. I think there's only 15 on screen though, because one is off screen here, it doesn't fit. And so we'll address that by only drawing 12 in a row. And that's great, but typically in space shooter games, there's more than one row of enemies attacking enemies. So I think we're going to have 3 rows or 4 rows of enemies. I think that would be a nice amount. In order to draw more enemies, and on each row, we're going to need a nested for loop. And to make this clearer to conceptualize, I'm going to be changing the eyes. So I'm going to press Control R twice to rename again. And I'm going to change the eyes to be X. And it didn't work. I'll change them manually. Old-fashioned way. Because what I want now is a nested for loop where in each column, so I'm changing this to Y. I said I wanted like 4 rows and 12 columns. We can do a similar syntax here for the Y position where we add, let's say since they are not as tall, let's do like 12 pixels of separation along the Y. So I'm going to put plus 12 times Y here. So for each row, make a column of 12 enemies and determine where their positions are based on the X and Y variables here. Let's see what that looks like. Excellent. We now have a grid of attacking enemies ready to go. Nothing special happens yet, but they are there. The next thing we're going to want to do, make it so the enemies are different. You'll notice that each enemy, if we look here, is the same. And this presents a conceptual problem here design-wise. Because if we look at the code, right now we're storing a list of positions for the enemies. So how do we specify a different type for each enemy? And you might be thinking, well, why don't we just draw a different subsprite at random for each alien? If you were to try to take this approach, let's say you you try to randomize what the aliens are by doing something like this. Alien number will be equal to a random value between 0 and 2. That's what this means. Random modulus 3. We'll pick a value up to 3, but not including 3. And let's say you had a switch statement like this. This might be one way you could try and do this, but there is a fundamental flaw with this. Then we can draw alien 1, alien 2, or alien 3 based on what was picked. If we were to try and run this, you'll see there are different aliens. However, they're flickering really fast. And what it's actually doing is every frame, if we were to pause this, it doesn't show. I would have to actually pause the game engine. If we were to pause that, though, I can do this, though. So here was a capture of it. We would see that the aliens are randomly being picked, but every frame they keep on changing and changing. And this presents us needing a new structure. We can no longer just rely on stuffing this in here, because our enemies have multiple properties. We want to be able to use a different type of alien at random, but we can't just draw randomly different sprites on the screen. And so one way we can handle this is instead of storing a vector 2D here, we store information about an enemy, which now makes us have to create a brand new class, or struct in my case. I'm going to use a struct that contains multiple pieces of data. We already know we need the position of an enemy, so that's going to be included in this struct. But now another piece of data we're going to need is what type of alien it is. And one way we can bring in what type of alien it is by using this rectangle. So I'm just going to label this alien sprite. And so we will choose the alien sprite when we create said enemy here. You can see it's already errored out saying, hey, wait a second. Enemies require an enemy now, not just a position. So the position can stay, because in our struct, we defined the first argument as position, the second one as the rectangle. So I'm going to type a comma here now, or we actually need a second set of curly braces. It's going to look a little confusing, but the first set of curly braces here represents the position. The second one will represent what type of alien we use. So that code where we picked a sprite earlier, we're basically going to use it again. We'll choose a random sprite or alien type between 0 and 3. Choose an alien number between 0 to 2, not 3. Then do a switch statement based on the alien type. And we have these cases here that are triggered based on which number was picked. Depending on which one was picked, we could copy paste this into there, or a little cleaner and smarter is to store a rectangle containing the alien's sprite. So we can set the alien sprite based on what what was picked here. So alien sprite will be alien 1, alien 2, and alien 3. We can apply the alien sprite into our enemy after that. I think this is a little cleaner than copy-pasting this over and over. This was something I was thinking of earlier too. The reason why I don't like this is because what if we want to change these values? If we want to change these values later, we have to do it in 3 places. That's pretty annoying, right? When we could just store a value of what the alien sprite is supposed to be, and then put that here when we create it. I think this is a little more clean, and I do this a lot, actually. I think I prefer it over, especially if you're going to be copy-pasting multiple times. So, just to recap, we pick a random alien type, which is going to determine which alien sprite we use, and finally, we push back our new alien sprite into here, which our alien object now contains 2 parameters, both the position and the sprite. Now you see down here we have a problem, because our enemies list used to produce vector 2Ds, now it produces enemy structs. So we have to change the type here to enemy. And now we can't just say draw subsprite of enemy, we have to say enemy.pos, because our first argument for draw subsprite is a position. The second argument is not alien 1 anymore, but is the enemy's alien sprite. We can now hit play here. Ta-da! Because the alien sprite is now tied to the enemy itself, when we reference it will draw that particular sprite on screen. The next thing we're going to do is add some game behaviors. We don't have any game behaviors yet. We're just drawing stuff to the screen. It would be fun to interact with the game a little bit now. Let's add some player input. We already store our player position in a variable here, so it's not fixed. We can change these to control where our player is, because our player position is being drawn at that appropriate coordinate. So by changing the player position, I don't want to be an on-user create, by the way. Anything input related is going to happen every frame, like we want to keep updating the position. So on-user update is where we're going to add the input stuff. In Pixel Game Engine, there are functions called getKey, which allow us to specify a key value, OLC key value. So I can type OLC : and choose a key. In this case, I want to control my ship by pressing A to move left and D to move right. So I'm going to say if getKey OLC_A.be held, these represent the state of the key, so we want it to pull when it's held down, not specifically when it's held or released. If this is true, we're going to be moving the player left. And to do that, the player position's X has to be subtracted. And not only does that have to be subtracted by some value, let's say we can move 32 pixels per second. We have to multiply this by the felapse time value, which represents how many seconds have passed since the last frame. And this is important to do because anything movement related needs to be based on how much time has passed for one frame. If our frame is running in the thousands of frames per second, then not including this value will make it zoom away, while somebody running on a slower computer would experience a very normal movement. Let's try to run this, make sure it works. And we can see holding left and right, something went wrong. For one thing, this line here indicates that we have not cleared the screen at all. And that's an important thing to do. Let's make sure to always clear the screen to a color. That way it's updated. We just haven't had any animation yet. So far, all we've done is draw a static image. When we start updating it, it's going to leave behind pixels as things move. The other thing I want to point out is that it just suddenly jutted across the screen like that. So what happened? Well, you can think of it this way. The player's x and y position are stored as integers, so we need to turn this into a float. So for the first time in this program, I'm going to be using the vector float2d parameter to represent a position. And this is better when you need precise movement, which we do for the player. We want to control it like so. So you can see now when I hold left and right, we do move. It's a little slow, so I'll speed it up a little bit. We'll do like 48 instead of 32. And so that works now, but that's not all we have to do. On top of being able to move, I would like the spaceship to be able to shoot, because we have to shoot at our enemies and destroy them. So we're going to be introducing another new set of parameters, new objects, called bullets. Yes. And we can do kind of what we did for the old set of enemies for now. We can define a vector here. And I already know that we're probably going to want to split this up into a separate class. We might include more properties for bullets later. So I'm going to make a vector of bullets. We have to define our new bullet class or struct. And for now, the position is all we'll need. We'll probably need more stuff later on, but we're just going to do that for now. Store the position of the bullet. Whenever we shoot, I'm going to say the spacebar will be for shoot. So we already know how to pull a key for that. Let's create a bullet. We know how to add things to a list. We just call the list, so bullets.pushback, and we have to specify a bullet. So we'll use the curly brace initializers. The first parameter is a position, so we'll put another set of curlies here, and we'll define that position. The position will be based on the player's position. So I can actually type player pause here to represent the position of the bullet. Now, we don't do anything to render bullets yet, and we also don't have a sprite for it. My intention for the bullet was to draw a straight line, just a thin straight line, pointing upwards. So for enemy, or for bullet, in bullets, we're going to use the draw line function of the Pixel game engine. The drawLine function requires two parameters at least, both a starting position and an ending position. Since we're drawing a straight line up, I'm going to be using the bullet's position to represent where the start of the line is, and then I'm going to draw a line straight up by subtracting another vector that is 4 pixels up from the previous director, or vector. So this is what it looks like. We take the position and we subtract a vector that has a 4. I should be adding it, not subtracting. Add a -4 to that to get the second point. So if I hold down space now, I have created, well, many bullets. I'm basically drawing pixels on the screen. And I'm holding down the spacebar. So technically, we're creating more and more bullets every single frame I'm holding this down. Like, literally thousands, now hundreds per second. And this is actually affecting memory. So clearly, we need something to limit how many bullets we create. And we also need something that says these bullets have to move. Because bullets move, right? They don't just stay there. So for the first time, I think we're going to introduce some function into a structure. Because we want bullets to move up, we want to define that behavior inside of the bullet class. Like the bullet should be responsible for controlling its position, right? Like its inherent movement. I think learning object responsibility early on, especially if you're dealing with object-oriented programs, like games, is very good. And the bullet should be responsible for moving itself upwards. That's its default behavior, and it should be doing that. So I'm going to be adding a new function called update. And typically in games, a lot of objects will be responsible for updating their own selves. So we're going to mimic what the onUser update function does and include an felapse time variable with the update function, because we're going to need that when we move. As we know, we want to move based on our speed. So I'm going to set the position of y minus equals a certain value. Let's make it pretty fast. Bullets are speedy, right? Let's try 96 multiplied by felapse time. Now, felapse time is known here, and it's also known in onUser update. So when we update the bullet, we can pass in the felapse time from the game engine's onUser update felapse time value over to the felapse time value in the update for a bullet itself. So nothing happens yet. If we try to run this, bullets don't update. They still stand still, because we still have to call it. So above the player input stuff, I'm going to iterate through all the bullets again, like I did down here for draw line, and include an update function. You might be wondering, so here's the update function, and pass in the felapse time value to it. You might be wondering why I didn't just do it down there, like this. I have two reasons for that. One reason is I like to keep all the updating happening before the drawing, as two separate pieces. Typically because the game state likes to change and things happen to it. So if you keep these separate, then let's say bullets only have to update when they are like on the screen, as an example. Well, I still want bullets to always be drawn, but maybe I want certain things to only happen when the bullets are on the screen compared to when they're off screen or when they hit an enemy. And if the drawing is tied to something unrelated to what's happening to the bullet, then we're going to have problems with it. And this explanation doesn't really do it justice here, but you might see what I mean when we add more complex behaviors later on. Keeping the update function here will allow us to produce more clean, maintainable code, instead of combining it together with the draw function. I'm going to go ahead and run this now. As this says, for every bullet, we're calling the update function. So you can see I've got this like little laser looking thing now. It's actually kind of cool, but we still haven't limited how fast we can shoot, so we get this constant stream of bullets going on. And it does look pretty cool, but you can see there's also a set of white building up at the top, and that's just how the engine handles pixels that are being drawn off screen. You'll see the implementation for a position, like if I type .x here. Actually, it probably won't show it here, but if I look here, where we used it earlier. No? You don't want to pop up for me? Okay. They use, where? Sorry, I meant to go here. The draw line function, although this is just a mess, basically says if something goes off screen, it's just drawn at the top. So when our position is 0, well, we're not going to keep drawing off screen like negatively. Instead, we just kind of get stuck at the top drawing pixels over and over and over. It's clamped to 0. And that's essentially what we're seeing there. It's just a side effect of how drawline works. To limit the player's shooting, we need to know when they last shot a bullet, and then say you can't shoot again for some amount of time. So we could introduce another variable called player shot timer. And we could set to 0 at first. And if it's 0, then we are allowed to shoot. And if it's not 0, then we can't shoot. This is a very easy way to handle timers, is you kind of incorporate it all at once. If it's 0, it has an implied meaning that it's not set yet. So we can go down here, and where we have holding down space, we're going to see if the player shot timer is equal to 0. If it is, let's add a bullet on the screen and set the player shot timer equal to how long we want to wait. In this case, I want to shoot a bullet every like 4/10 of a second, like 0.4 seconds. So we'll say the player shot timer is now 0.4. And this allows us to shoot once, but we also need to make it so the timer counts down so we can shoot again. So now we kind of need a player update function. And you can sort of see here a pattern emerging. The player needs an update function as well, but we don't have a player class yet. So instead we're doing player shot timer, and we just, we're going to be using the standard max function. What this does is it chooses between the values provided, which one's the highest. This is like a trick for an if statement, where we can say subtract f-elapsed time from player shot timer, and then for the max function we also include this 0 value here, and it needs to be a float, so I'm going to add a decimal point and an f to make it a float. This little trick is the same as writing if player, or it's the same as writing this, player shot timer minus equals f-elapsed time, which would be what we wrote here essentially, and then seeing if player shot timer is less than 0, set it to 0. This right here is the same as this, and is essentially what it's doing. Because if we can choose between picking 0 or this, whenever player shot timer minus this is negative, 0 will always be picked. So we're essentially clamping it to be 0 all the time. And so this is a very compact way to write that statement. And we like it when we can simplify our code. Keeps it nice and clean. So let's take a look. If I hold down space now, it's now shooting a bullet every 0.4 seconds. It's really fast. In fact, I think it's too fast. So I will slow it down quite a bit now. I'm going to go back up to the bullet, and for position.y, I'm going to make it go down by, let's say, 32. That way it's not zooming. It's still pretty fast, though. Unusually fast. Like, let me try 1 here and see what happens. Because it is... You can see it's just like zooming across the screen. This is very unusual. It's almost like I didn't change anything. Well, what is happening? At least the timer is working, but something is going on here with the bullet in terms of updating. Which is very strange, because this should not be happening. Basically the same thing as the player. We might notice again the position is represented as an integer, right? And if we deal with anything related to f elapsed time, we make a float. And again, if we multiply 1 times this, we're going to get some crazy value. So once again, change this to a float. Now you have proper control over this. So it's just a matter of using floats for positions. We can see now it's very, very slow in comparison. So we'll put it back to what it was before. But yeah, this is what the expected speed was supposed to be with the 96 here. Ah yes, this is a much more manageable speed, and it looks like we can shoot bullets just fine. Nothing happens with the bullets yet in terms of collision, and bullets that go outside of the screen remain forever. They're not deleted yet. We'll have to handle all that soon. But let's first work on the collision here. Bullets that we shoot need to check every enemy and see if that bullet is in range of that enemy. I think the easiest way to implement collision is to use circular distances, or radii. Circles are very nice and very easy to work with and very fast. So I think we'll be using that for our collision, but we have to think a little bit about how we want to implement this. Because right now, we're iterating through all of our bullets, and we're updating them. But in order to check for collision, we also have to iterate through all the enemies and check for collision that way. So we already know we're going to need a nested loop here, where we iterate through every enemy. For enemy, enemy, inside of enemy, we have to do this. But this will have a side effect. For each enemy, we would be updating every bullet every time. So we can't do it right here. I think a nice alternative is to think about it the other way. The way I said it the first time is for every bullet, iterate through every enemy and see if we collide with them. Now, how do we know if we collide with them? Well, we're going to check the distance from the enemy. I'm going to make a new float variable here so I don't clog up the if statement. Distance from enemy equals, and we're going to be using the distance formula, which is taking the square root. So I'll be using square root here. I don't think I need standard, actually. Taking the square root of the squares of the differences of the positions added together, which sounds like a mouthful, and I mean, it's math. So for this particular bullet's y minus, or you can do x first. I think that makes more sense, actually. Do the x's and then the y's. Take the enemy's positions x, and we have access to both of these, by the way, because we're in a for loop with both a bullet and an enemy at the same time. And we're going, the second argument of pow is square. The second portion of this is bullet position y minus enemy position y squared. Take all that, do the square root of it, and boom, you got the distance from the enemy. It looks a little complex, and yeah, it is some math. You can look up the distance formula. That's how you would implement it. Now that we know the distance from our enemy, we can check it. If the distance, and this will be in pixels, so the bullet is 4 tall, and the enemies are, how large were the enemies? 11 by 9, 12 by 6. I mean, they're pretty big. They're pretty fat. So for a distance, let's say if we're within roughly 7 or 8 pixels, I'll do 7 for now. If distance from enemy is less than or equal to 7, we've hit them, so let's destroy them. Now, saying that is more easily said than done, because, for one, we're looping through a list. If we were to just delete an enemy from this list, it would cause the iterator inside to become invalid. So unfortunately, it's not as simple as just delete it from the list. A very common way to handle this in video games is to mark them as dead. I would like our enemies to have health, by the way. So I'm not just going to have them mark as dead, but I'm going to be adding a new value called health, and I'm going to set it to 1 for right now. But I do want some of our enemies to have health later. You might have saw in the example that when I shot an enemy, it changed color and its health got reduced by 1. We're going to be doing something very similar here. So setting the health to 1 for now just makes it have 1 life. So if distance from enemy is less than or equal to 7, we actually want to hurt the enemy. And so a typical way I implement this is by having the hurt function return whether or not they have died. So we're going to hurt the enemy by including a hurt function available inside of the enemy. So I'll call this a Boolean function hurt that returns true if the enemy has died. And it would be nice to specify how much damage we do to it, but for now, I'll just default it to 1. I'll say, if you don't specify anything and you just hurt the enemy, it'll do 1 damage. And when we get hurt, we subtract our health from damage. And then we return whether or not our health is greater than, or if our health is less than or equal to 0, then that means we died. So right here, this is a very powerful function. We can specify how much damage we deal, and we know whether the enemy is still alive or dead after this, so we can do something with it. And my original thinking for this was to write something like, if hurt 1 damage, because it'll be 1 damage, so if enemy hurt is true, then we can mark that enemy as ready to be deleted. So we need another variable that says, I like to call this alive or active. So by default, enemies are alive. They shouldn't be dead at the start. And then if they get hurt, it'll set their alive flag to false. And originally, I was thinking this might be the way I implement it. But it's kind of counterintuitive, right? If the enemy hurt function and whether it's alive or not are bound together, we can think of these two things happening internally instead of doing it out here. See, we're in the shooter game class, and the enemy is responsible for keeping track of whether or not it's alive or not. It should know whether it's alive. The game class should not care about controlling whether the enemy's alive or not. That's an implementation detail that only the enemy is concerned about. So what we want to do instead, at least I think this is much more preferable, is just call the hurt function here, and internally the enemy decides if health is less than or equal to 0, it's not alive anymore. See, in my opinion, this is a lot more powerful because now we don't care outside of the enemy if it's alive or not. We just care about hurting the enemy here. Bullet meets enemy, hurt it. If the enemy dies during that, that's what the enemy cares about, and only the enemy cares about setting whether it's dead or not. Try not to include too much code unrelated to the game itself outside of the structures that need them, because it's a very subtle thing to think about, and it's going to be very hard to find these things at first, but it's going to make the code a lot cleaner because we're not typing as much out here. We're instead hiding away the little details inside of things like this. So a hurt function not only damages the enemy, but determines if they're alive or not. Now we have the ability to delete stuff after we're done iterating. Since we can't delete stuff while we're iterating, let's delete stuff afterward. The C++ standard library has some weird quirky ways to delete stuff from a list. However, the simplest way to handle it is to say enemies.erase or bullets.erase and provide a position. However, in order to do this, we would have to, again, iterate through all the enemies and see if the flag is set to determine if we delete them. So we run into the same issue. We could use what are called iterators and handle the iterator properly, but actually C++ has another built-in nice way to delete stuff from a list. And that is called remove if. So standard erase can accept an iterator, and when I say iterator, I just mean a list's references which it goes through to give you to point to like all the stuff inside of it. They're all just references and pointers in the end, wrapped up in a nice package. Standard erase, standard remove if. This is gonna look a little scary. But we're gonna try this out because this is a very powerful way to remove stuff from lists based on a condition, which we have a condition, by the way. But this syntax is gonna look really bizarre at first. But I will explain it. This should be right, but apparently it's not. So I will go to my handy dandy CPP reference and just make sure we didn't forget an argument here. It looks to me like I forgot the actual it looks to me like I just added random stuff at the end, because I did. Oops. Okay. So what this is the beginning iterator and the end iterator of what we are trying to check for. So what we're checking for is whether or not an enemy is still alive, right? So the enemy gets fed inside of here. If I type in enemy E, we now have a reference to the enemy. I'll type out enemy here, just to be a little more verbose. And we're going to return if the enemy is not alive, then we can mark it for deletion. This is called a lambda function and is typically included in a lot of these, like what are called function templates, where we provide all the functionality of it inside of the function as an argument. So it does look a little scary, but you can see here in the standard or in the CPP ref that we kind of do the same thing. Oh, I put standard erase, my bad. That's what's wrong. Enemies.erase. So we say remove from enemies if and not enemy alive. And I will show the other way just for the sake of learning. You can do this with iterators by doing it like this. So you say for auto enemies or auto it equals enemies.begin. This starts the iterator at the beginning of the list, and we're checking for it being not equal to the end of the list, and then we're incrementing the iterator by 1, because they're pointers, so if you increment them, it goes to the next item in the list, essentially. And the way you would do it this way is you would grab the enemy reference using this kind of bizarre syntax where you do what's called dereferencing to get the value from it, which turns out to be an enemy because it's from the enemies list. And yeah, this is a lot of like weird jargon syntax stuff at this point. I'd say if you're still learning, you're best to just stick with using it for now as a black box and just understanding inside of here is how we control what gets deleted. But yeah, the other way to do this would then be to see if it's not alive anymore, then we have to remove it from the list. So you see, again, we would be using erase here, but since we know where the iterator we're erasing from is, we just type it here, and because it has shifted over, we get a new it value, and then we check if it's not equal to, or if it is equal to the end, because it might be, then we have to break out of the loop, because otherwise we might end up in an error if we increment it here at the end, and yeah, you can't go outside the end of the list. So this code would break unless we included this if statement here at the very end. And yeah, this is pretty messy either way you do this. So I like this clean one-liner here. It's still a little archaic syntax-wise, but don't worry. Over time, you'll become more comfortable with either of these methods, and it'll be a lot less daunting to do this. Yeah, the key takeaway is this condition where we say, remove stuff if the enemy's not alive. So, interestingly enough, this should just erase enemies from the screen now if Able collides with them, assuming we don't run into errors. The vector erase iterator is outside of the range. What could that mean? Well, let's have a look. To use the debugger, when this happens, you just hit retry here, and you'll get this. Now, it looks a little scary at first, but down here, I have a list of the call stack. And if you don't see this when you click this, then the way you can bring it up is by going to Debug, Windows, and clicking, it's probably in here, call stack. That'll bring up that window. There's a lot of other windows here. So if you see a window on my screen that doesn't exist on yours, that's how you would bring it back up. The call stack tells us what lines of code were executed and how far it got. So in here, this is actually the standard vector from the standard library. 99.99999% of the time, your bugs are not going to be because the standard library is coded badly. It's almost never the case. So what we do is we go to the call stack and look at where our code is. In this case, if I click the second one, it takes us to on-user update, line 94. Boom, here we are. So the second argument of this is the end vector. And so if I add an end vector here, which I did in the reference here, what that says is that if this is the end vector and it goes to the end vector, or end iterator, then we know for sure that it's just not going to do anything, because the end iterator is at the end of a list. Boom. You can see the program actually runs now. But this is important because erase removes from a range. So remove if says everything from the beginning of this part of the iterator to the end gets removed instead of just something we specify here. I guess it's not super important to know the details about that, but again, it's more syntax that needs to be included to make it work right. I didn't actually show the shooting here yet, but if we were to shoot and we were to hit one of these enemies, you can see the bullet never disappears. And the bullet never disappears because we don't tell it to disappear. But we can make it disappear in much the same way we did for enemies. So when the enemy gets hurt, not only does it hurt the enemy, but it also deletes the bullet. So the bullet needs an alive flag just like the enemy does. So I'm going to add the same thing here. Alive is true. And when we hit an enemy, it sets alive to false. I do want to keep another, like, we'll say a kill function, if you will, which sets alive to false here. And just call the kill function instead of calling alive directly. So call the kill function here, bullet.kill. That will mark the enemy for deletion. And then we can, like I said, you can treat this as a black box. If you were to copy paste removing enemies, and instead you remove bullets, well, now you've pretty much solved that. The only thing is you have to change what the incoming object is, so it's a bullet, not an enemy. And we want to remove it if it's not alive anymore. So the exclamation point means not again, and alive. So like I said, if you're not understanding the syntax, you can mostly use it as a black box and just change what the function inside is called. And that removes it from the list that way. So here now, the bullet and the enemies get removed, and we have the shooting done that way. So that's pretty good. And the collision is very simple because we're just doing distance checking, and I think it doesn't need to be anything fancy. We don't need any like rectangle collision checks, which usually require 4 checks to see if the corners of both bounding boxes are aligned. It's not quite needed for a bullet of this type or a game of this simplicity. The next thing I want to do is make the enemy have different health, but I want the health to be based on what type of alien it is. So we were here in the switch statement where we selected what alien sprite we wanted to use. We can also define its health. Its health is the third parameter and is set to 1 by default. So if I were to type comma 1 here, we would be setting the health of the enemy. And we can control that as well based on the alien's type. If I specify an int parameter here, and I say alien health, we can say when we randomly select the third alien, its alien health will be equal to 3 instead of 1. And alien type 3 is the should be these look no, not these guys. It should be these guys with the blue eyes. So if I were to try to hit them now, you'll see it actually takes a couple of hits. Oh wait. Why are they taking 3 hits? That's not good. Why are they taking 3 hits? It appears I may have goofed because I hard-coded the 3 instead of typing alien health here. Alien health will be set to 1 for all alien types by default, and then it changes to 3 when I type this, like so. Be nice if I'm actually shooting them, huh? And then these ones only take 1 hit. And same with these types over here. So that works well. It would be nice if they had a little bit of color to them, which is actually why I chose white. I specifically chose this white color so that I could blend them with different colors. So let's say when we hit the enemy, it will be, or let's say if the enemy has more than 1 health, we color it red. And if it has 1 health only, it'll be colored that a green color. So right now we specify draw sub sprite to handle our drawing. If I go to the draw sub sprite function again, it calls draw partial sprite, and one of the arguments for Well, here's what I wanted to do. I wanted to do some coloring, but you can't do that just with draw sprite. You would have to call draw decal, and decals are a little more fancier, but they allow us to color a sprite a different color. So draw partial decal, luckily, uses pretty much the same syntax, position, size, decal, source pause, source size. The difference here, I think, is size. The size of the sprite needs to be specified here. So we just do sprite width and sprite height again. Tilesheet. So we're using, and unfortunately, this also requires a decal. So I'm going to be changing the entire project to be using decals now. I think this is a really good time to do that, as decals allow not only render on the GPU, but they also allow us to do other fancy things in the future if we want to. So they're a bit more flexible. What's kind of cool is that we did draw sub sprite for these functions. So it's not like we have to redo our drawing subroutines. We just change in here what we're doing, and every sprite gets updated accordingly. So that's a nice touch to modularizing some of our code that way. However, we get stuff like this, where we were relying on integers before, and now we have to explicitly convert them to floats. So in here, not only do I have to specify width and height, but now they have to be floats as well. So the easiest way to do this is to change all of my vector integers to float and change my rectangle to use float values instead. X, Y, width, height, all floats now. That way we don't get any problems with conversions. The other way you could do that is by casting, which is what I was thinking of doing, but you'd have to go around casting this everywhere like this, and it can be quite annoying. So seeing as everything uses the X and Y from sprites themselves, I think that's the best way we could handle this. And it couldn't convert all the arguments of the pushback, that's what it's telling us, for enemies, which happened here. And the reason it did that is because this wants a float now, but we were specifying integers. So once again, it's a float issue. And an easy way to fix that is to specifically say this is now a VF2D in front of that. And now these require narrowing conversions by being floats. If you add float to any of these numbers, it will automatically turn it into a float, because once you add a float and an integer together, it's kind of a subtle thing, but it makes it so it returns a float. So I think that's better than doing this, actually. That's now optional, because it'll figure it out from there. Woo! That was quite a bit of work. But now we're going to have the ability to color sprites, because decals have the ability to do some image blending. So I'm going to type comma again here, and now we get this tint parameter. Now the color is going to be based on the health of the enemy. So I'm actually going to create a new OLC pixel, which is a color, and I'm going to call it color. The color will be green if the health is less than a certain value. Now notice we can't access health right now. All we have is a position, like an enemy or player position, and a rectangle to draw a sprite from. We have no clue about what the color information is supposed to be, so we actually can't check for the health here to determine what color the sprite would be. In these scenarios, you have to pass it in as a parameter and handle that check elsewhere. So whatever color we specify will be the color shown here. So we go down here now. Both of these are out because they need some default color. For the ship, I'm just going to use normal blending, and that's going to be white. In fact, I think it makes sense for it to always be white unless we specify otherwise. So add a default parameter here, and then I don't have to include this by default. But I still want to use coloring for enemies. So you can see, aha, now we're in an enemy loop, so we can check for health. So we can say, if enemy health is greater than 1, we want to draw it with a red color. Otherwise, we want to draw the enemy with a green color. So you can see now we kind of got this like Christmas tree going on of enemies. So when I hit these red enemies twice, they turn green. And we can even go one more stage. We can make them turn red when they have 2 health. So if enemy health is greater than 2, make it red. Else, if enemy health is greater than 1, let's make it yellow. And otherwise, it'll be green, because it will be 1. So hit once, it turns yellow. Hit again, it turns green. Hit again, it disappears. So we can see now we have health on some of these enemies, and we have a visual indicator of how much health they have. I think the final thing to do is these enemies are kind of boring. They just kind of sit there and let us kill them. We should make it so they move around, making it a little harder to hit them, and maybe do it Space Invader style, get them moving closer to us over time. We're going to be adding this zigzagging motion, and so we're going to need a couple of little extra tools to do that for us. So we're going to need a parameter that tells us how much we're offset by. Like, we're going to take the whole field, all the enemies, and offset them by a certain amount each time. And the way I want to accomplish this is there's going to be a variable that determines where in the pattern all the enemies are at. Let me represent this with text real quick. So if we have a zigzag state of like 0, we would say that's the start, right? And we'll have it so it counts up, like 0, 1, 2, 3, 4, 5, 6. As it counts up, we're going to say the enemies move towards the right. And then when this hits a certain number, we're going to say, okay, you guys are too far to the right. So we're going to move down 1 and then start counting back down to 0. So this will oscillate. It will go up, it will come back down, and then it'll go back up, and then it'll come back down. And each time it does this, the enemy wave moves closer and closer to the bottom of the screen. So this is the behavior we're trying to implement. So we're definitely going to need something to indicate how far along this track we are. So we're going to call this the enemy move amount, and we'll start it at 0. I think that's a good name for it. Enemy move amount. It makes sense. We also have to know which way we're moving. You'll see here it's incrementing and here it's decrementing. So we need some way to figure out, do we go up or down when we're moving? So moving right will be a Boolean that we start by saying true. So when we set it to false, it means we're moving to the left. That's what it implies. Finally, we don't want the enemies just moving like really fast and every frame. We want them moving every so often. So finally, we need a timer for this movement as well. Moving or enemy move timer. And we'll use it just like the player shot timer, I think, is the best way to handle this. And notice I'm putting all of these in shooter game. I think the game should be responsible for handling this timer as it moves everything. Sure, it's the enemies that are moving, but the timer applies to all enemies, and so it's a behavior inherent to the game itself, not to an enemy. So another thing to think about when it comes to who's in control of this, right? You'll notice I'm doing a bit of scrolling now. The file's getting a bit lengthy, and I recently just did a video on how to split things up into multiple files, so you're not scrolling around everywhere and making your source files unwieldy large. So, do check that out as well. Uses the same game, actually. So what we're going to be doing here is using these three variables: enemy move amount, moving right, and enemy move timer. Firstly, let's incorporate the timer again. Kind of like we did for the player shot timer, we can have it count down when it's greater than 0. So we'll just replace these with the enemy move timer instead. This makes it so it counts down towards 0. So if enemy move timer is equal to 0, we know that we have to adjust enemy move amount based on moving right. So if moving right is true, then we're gonna set the enemy move amount by increase the enemy move amount by 1. Otherwise, we'll decrease the enemy movement amount by 1. And on top of that, we need to set the enemy move timer when we do this to how long we want to wait before moving again. I'm going to say for now, let's move the enemies every 0.8 seconds. So we'll set the move timer to 0.8 to wait that long before trying again. So this should make the back and forth movement. Let's take a look. Well, it would move, but the enemy move timer apparently is not triggering. Interesting. At least you would think that, right? So what's actually going on here? Well, let's use the debugger. Is this triggering, first of all? If we want to find that out, we can place a breakpoint anywhere in here. And nothing's stopped, which means this doesn't trigger. Well, is our on-user update working? Of course it is, because the game's running. But we can click here, and we can see suddenly our program stopped at this breakpoint. So I'm now going to click it again to turn it off and hit continue. Using the debugger can be very helpful. What we want to find out, though, is why isn't enemy move timer being set? So we'll pause here and take a look at enemy move timer. You can mouse over things and see what their values are. Well, that's strange. Enemy move timer is 0.16 right now. And if I hit continue here, it'll trigger again, and now it's 0. So this is kind of a bad example here because if you pause it, then obviously that amount of time has passed, so the next move timer will keep running and running. But let's put a breakpoint here again, and put a breakpoint here, and then I'll hit continue. So you can see it still hasn't triggered. So let me put it here. Before the conditional, you can see now it's triggering. It, line by line, it's going through here to here, and then comes back up to here, and it's triggering again. So we know enemy move timer is actually running because we can pause it and see after every 0.8 seconds, it does trigger. What we don't understand is why it's not updating anything. And for that, we have to go down here and notice that we are updating based on the enemy's position. We haven't incorporated the enemy movement into here yet. Oops. So let's fix that. When we move or increment movement amount, we have to move every enemy. So we're going to be using this syntax again to loop through all enemies and say, oh, I put E. I'm trying not to abbreviate here. So we'll say the enemy's X position will now be incremented by some amount. Since they're separated by a grid of 16, I think it makes sense to move them by 16 pixels as well. That makes the most sense to me. And we can do the same for the opposite. When we set the enemy movement amount back, we also subtract from the enemy's position. Ah, yes, you can see now they are moving off screen forever and ever and ever and ever. Yes, not quite the zigzag pattern we want, is it? Well, we haven't implemented a a way to handle moving backwards, so we have to do that now. When we move up, forwards, or back, we need to see if the amount is greater than a certain amount. So if enemy move amount is greater than 5, because we said 6, right? Was what I was thinking originally, at least. Then we have to flip moving right to be false. So this is like a shortcut way to do that. But this is basically me saying moving right becomes false. So I'll be explicit here so it doesn't look confusing. And here we're subtracting. So if enemy movement amount becomes less than 0, we set moving right to true. Let's take a look now. Because essentially this number is going to go... Uh-oh. Yeah, they kind of go off screen, which is not quite what we want. Which means there's too many movement cycles here. They go 6 times to the right before coming back, but there's clearly not enough room for that. They've only got room to move right like 4 times. 5, 6. So you can see it's a bit much. We're going to say if the enemy move amount gets to greater than 3, we'll start going backwards. So 0 to 3, back to 0. So it's moving 4 times still, because 0 to 3 is 0, 1, 2, 3, and then it goes 2, 1, 0, negative 1, so on and so forth. So I'm going to put an equal sign here, because when it hits exactly 3 now, not just when it hits 4, it'll start going backwards. So just a little bit of tweaking here. So they go to the edges of the screen and make their way back. And so we now have this zigzag pattern. Now we just have to add the down moving pattern. And the way we would handle this is before checking for moving right, we actually see if this is true first. So I'm going to kind of flip it now and say, if the enemy move amount is greater than or equal to 3, we're going to reverse the direction and we'll set all the enemies to be a little further down on the screen. So something like this. Move the enemies down 12 pixels, and then we'll say else do what we did before. I don't want the enemies to move to the right and go down at the same time, or move to the left and go down at the same time. So I'm going to add this else statement here, which makes it so it doesn't do that. And then I'll do the same thing over here, where I'll move this if statement above it, set the else over here, and finally move the enemies to go down 12 pixels, like so. It's a bit condensed code, but this is one way you could implement a zigzag pattern. You can see now they move down, because what's happening is every time they're told, okay, I can move now. So first they're going to see if their condition is on the edge of the screen. If their move amount is on the edge of the screen, then yes, move them down instead of moving them right or left. So they have to make a choice here with this conditional statement. And I try to indent it as best as I can, but it does look a bit unwieldy. If you really wanted to, you could space this out a little bit better and have a better idea of what's going on there. So if we're moving right, then do this block of code where we then see, okay, if we're at the edge of the screen, change directions, move down. Otherwise, move across. So yeah, if it does look a bit too unwieldy, sometimes it's as simple as spacing things out better so you can see everything a little more comfortably. Some folks prefer formatting it in other ways, but this is fine right here. The compiler doesn't care about syntax. The syntax is for you, the programmer. So make it feel right for you. So I think we've done it. That is everything I want to cover for the shooter example game. I know it's quite a bit. I plan to do more videos covering all sorts of different types of games. So you will see these patterns come up again and again and again, and you will start seeing some commonalities. Every game utilizes very, very similar ideas. And I think we covered a lot of topics, so hopefully you at least can learn and utilize some of these topics to try and build a little game yourself. And there are going to be things that you don't understand. Yes, I used a lot of features today. I added custom functions. I added custom classes. We initialized those classes. We used containers. We iterated through those containers in quite a few places. We also deleted from those containers using special fun C++ template syntax and lambdas. We also used input control. We used timers. We used the concept of timers. There were a lot of things to unpack today, and this really shows, like, in my opinion, why games are so complex and why they're such complex machines, because they have all these moving pieces that you have to put together. And I think as we make more games, you're going to see some more common things between them, and that's going to really start showing, okay, this is what's important. This is what I have to learn. And of course, everything we covered today is important, but some games, you'll see the same things popping up over and over. So you'll realize, hey, we need to be using this structure in all types of games. Yeah. And you see we even started with this rectangle struct here. I started with the concept that when we have data that needs to be organized a certain way, in this case, positions and sizes, let's not create a bunch of variables for them, but wrap them up in a nice container that describes what a box looks like. So a rectangle, which has an X, Y, and a width height. Yeah, pretty nice. For those of you that watched, thanks for watching. Hope you all enjoyed. We now have a little Space Invaders shooter demo, essentially. Very good.